выдающийся ученый, профессор института MIT Томми Яаккола с лекцией «Масштабирование структурных предсказаний».
All right. So I'm Tommi Jaakkola. I'm a professor at MIT, primarily working on machine learning topics. Now, I don't have any understanding of the audience here, so some of the slides will contain equations, but I will try to convey the intuition rather than all the details of those equations. So I'm hoping that many of you ask lots of questions so that we can actually focus the talk on the right level. That gives me some feedback of how much you are understanding of what I'm trying to convey. So the topic of the talk is scaling structured predictions, so scaling predictions over complex objects. And this talk contains material from several papers with parts in collaboration with people listed here. Right, so over the past decade or so, machine learning has undergone transformation from essentially focusing on predicting labels or one-dimensional quantities and understanding the theory of it to making predictions over more complex objects. So the complex objects may be, say, natural language processing. It may be a segmentation of a word. That is a prediction that you're trying to get. Parse for a sentence. That may be the prediction. Labeling of an image, segmenting an image. Predicting disparity map or the depth field based on two images in the stereo reconstruction area. In molecular biology, predicting molecular structures. The structure itself is now the prediction that you're trying to achieve. Reconstruct pathways from data and so on, all the way to interface design. So this has really surged in popularity in machine learning over the past decade or so. So let me take a couple of examples just to highlight exactly what we are doing in this context. So what is structured prediction? So here's one example. Example in natural language processing, dependency parsing. So you're given a sentence that is the input, the X input example. And what you're trying to reconstruct is a parse tree, directed tree over the words in the sentence. So the tree itself is now the prediction that you're trying to attain and learn to make such predictions on the basis of examples of such sentences and parses that you may have. All right. Another example might be stereo reconstruction. Here you're given two images taken a little bit apart. And if you put those images back together, then the pixels have moved because of the different locations that the images were taken. As a result, there's some disparity in the locations of the pixel, and that disparity combined with the image locations allows you to reconstruct what the depth of each pixel might have been underlying those two images. All right, so the input in this case is the pair of images, and the output that you're trying to predict would be a disparity map or the depth field over the image. Here's another example, essentially in the context of web page design. You might have two web pages here. They contain different semantically meaningful locations. So login information, some help information, maybe advertising and others. And you have several instances of those web pages. So if I give you any pair of two, what I would like to get as the prediction is a semantic alignment of the two web pages. So it aligns the semantically corresponding pieces in the two web pages. All right? So from pair of web pages, the prediction that you're trying to make is an alignment. All right? So that setup hopefully is now clear. You're getting now complex objects as inputs and complex targets for those inputs, and you're trying to find a mapping from the inputs to outputs. All right? It's a standard machine learning problem, but now the complexity here comes from the complexity of the objects involved. There are a lot of commonalities here in terms of the underlying goals and challenges that we have in making these type of methods actually useful in practice. So in terms of goals, we would like to consider richer classes of structures. We would like to be able to exercise refined control over how those structures are obtained as predictions on the basis of the input examples. Put another way, we would like to entertain more complex mappings from the inputs to the classes of structures that you are predicting. And so here are the goals that I just mentioned, but these goals bring a lot of challenges with them, and it is those challenges that I would like to focus on today. So for example, considering richer structures often has the consequence that the combinatorial problem that you have to solve in order to just derive the prediction for any particular input can be provably hard. All right? So there's no polynomial time algorithm that's likely to solve that problem. If the prediction itself, just for a single input, is already hard, then how are we going to learn such models from potentially large amounts of data that may be available? All right? Richer structures also bring a challenge, which is dealing with ambiguity. As you're considering richer structures, parse trees, and other things, then little changes in the structures may not have any changes in the scores that you're obtaining for those structures. All right? So there's a lot of ambiguity what exactly the prediction should be for any particular input. All right? And I'm going to try to go over with some detail, hopefully conveying the intuition here, how we might be able to address all of these problems in order to make these methods more scalable. All right? So let's start with the natural language problem, dependency parsing. I mentioned earlier that given the sentence, you're trying to get a directed tree over the words in the sentence. So the meaning of that tree is that you take head word of each phrase in the sentence and look at which other words modify that word. All right? So it's the arcs in the tree are word modifier links in this case. All right? In typical languages, these parse trees actually are something called a non-projective, so the arcs that you draw might actually cross. And if they don't cross, the problem is combinatorially a little bit simpler. All right? So the goal for us here is then to find a mapping from the sentence to such structures such that we can score any alternative structure here on the basis of what we are given, the sentence. All right? And then make the prediction as the highest scoring dependency parts. All right? Everybody with me so far? All right, so let's translate this problem a little bit further. So if you take we can represent those trees by introducing binary variables. There are variables that just tell me whether I select a particular edge. So this matrix here is the words in the sentence and the words in the sentence. And there's a beginning word, the star, for each sentence from which this directed tree starts from. All right? So once you specify these binary variables, the values on that matrix, subject to the constraint that it has to be a directed tree, then it will be one valid candidate structure in this context. All right? So that's a representation of how we select structures. Then we have to be able to score those structures given a sentence. And the scores here map the input sentence to something that we can score the structures with. So in this case, we are looking at scores that simply assign a value for each arc, each directed arc here, between any two words, given the input sentence. All right? And these scores are parameterized, which means that I have to learn how to score, given the input sentence, each arc in the potential tree. All right? These features here that mediate from parameters and the sentence to the scores may depend on, say, just the two endpoints of an arc. What is that word that it tries to modify? Or it may depend on, say, the context in the sentence. Right? So once we have the scores, then what we are going to do for prediction is find the maximum score, select all the edges in the parse, find the tree that has the highest score, and this component here merely states that I have to select as a prediction something that is a directed tree. So it excludes everything else that is not a directed tree. All right? Now, the complexity of solving this problem depends on how we choose to score the different structures. All right? So what I've shown you so far is something called an arc-factored model, which for any given sentence just summarizes the input sentence as scores for each possible arc here. All right? So, for example, what it does not do is to couple the selections of arcs. So the scores don't change if there is one arc already chosen in the tree. All right? So in this arc-factored model, it turns out that you can solve this problem in polynomial time, make the prediction in polynomial time, by just applying standard maximum weighted directed spanning tree algorithms, the Edmonds algorithm. All right, so far so good. If this is how we could do parsing, then we'd be done. Unfortunately, that's not really the case. In practice, in order to generate good quality parses, we cannot summarize the sentence into just scores that depend on the arcs themselves. We have to couple the arc choices together. All right? So this is something called sibling scoring. So you take a word and look at all the outgoing arcs from that word. So look at all the other words in the sentence that modify that word and select those as a set. All right? So that individual problem, just maximizing that individual score here, may be still computationally tractable. You might have a Markov model of all the words preceding and all the words after that particular word and decide how to score their arcs. But unfortunately, even if they individually might be tractable, when you put that together with the tree structured constraint, you will get a combinatorially, often get a combinatorially hard problem. All right? And it's almost as soon as you move away from this per arc scoring that you go from a quickly solvable problem to something that's hard. All right? So somehow we have to address this problem. All right? Here's one particular methodology that we've been following in solving these type of problems. The methodology is called dual decomposition. So here's just the starting point of that, which is a decomposition. So think of the parsing as consensus predictions from a set of different experts. All right? One expert is just that per arc scoring method that we can solve in polynomial time. If I had per arc scores, I could apply just the top expert. It would select a parse tree for this sentence. Each of the nodes here are these outgoing arc experts. So just myopically would pick from each word, pick the highest scoring outgoing arcs. All right. The problem here is that the predictions individually would not agree. All right. There are experts that disagree, so we have to enforce agreement in some manner. And you can enforce the agreement by essentially introducing Lagrange multipliers for equality constraints between these experts, that their predictions of what the highest scoring structure is should agree across the experts. All right? So intuitively, all that this is doing is if you take a particular word and it really prefers a particular set of outgoing arcs, but the tree expert here does not like one of the edges, then you simply take one of, part of that score from this expert and move it here. All right? As a result, this still prefers that outgoing arc, but now the tree does as well. And you establish an agreement. That is what the Lagrange multipliers are doing here. All right? So just algorithmically, just to show that this is actually very simple to implement, here's the whole algorithm. We have the tree expert. In each round of the algorithm, the tree expert finds the highest scoring tree based on the scores that are factored according to the arcs. All right? That's the problem we can solve, polynomial time solvable problem. Now, for each word, we do the same thing. Based on their current scores, you find maximizing outgoing arcs. All right? And then you compare these answers. If they disagree, you modify, you take away from some, you add to another in order to establish agreement. All right? And if an agreement is found, then indeed the solution that we obtained in this simple agreement fashion is guaranteed to be the optimal to the original problem that was computationally hard. All right? So we can be expected to solve these problems optimally in every single case. The question is whether the practical problems that we actually have to solve can be solved fast in this manner. All right? So there are two parts to an evaluation of such a methodology. One is, are the parses that we generate with these more complex scores actually meaningful in practice? And I'll just state the answer to that as typically yes. So you get high quality parses. The second part that pertains to the approximate method here is how often does it succeed in finding the structure that the model actually prefers. All right? It is an approximate method, but then sometimes you get provably optimal prediction. And this is just a table across languages that demonstrate that in maybe on average 97% of the time, this actually solves the combinatorial problem correctly. All right? So the message here is that even if the combinatorial prediction problem is computationally hard, practical instances may still be very much solvable optimally. All right? It depends on the structure of the problem. All right. So that's one challenge, how to just make a prediction. Now we have some tools to make optimal predictions over more refined models. All right? Then the second challenge here is that we'd like to learn these models from large amounts of data. But if the individual prediction is already hard, then maybe learning these methods from data is even harder problem. All right? So what I mean by learning in this context is if I'm now given pairs of input sentences corresponding parse, input sentence corresponding parse, I would like to optimize the scoring function here, how the args or the larger sets are scored, so that for each of these training cases, roughly speaking, I would get the correct target answer. So I'm going to use the training cases to narrow down the set of possible scores that work well as far as the guidance from the training examples is concerned. All right? Another example would be in stereo reconstruction in the same setting again. Inputs are pairs of images, the outputs are the reconstructed depths, and based on these pairs of examples, we would like to optimize the scores in the same way. All right. So how do we solve this problem? Well, I've emphasized already that just to make a single prediction is already quite hard. The question is, can we somehow get the parameters much more cheaply than the cost of making a single prediction? All right? Unfortunately, in general, the answer is no. So if the prediction problem is hard, then the learning problem is hard as well. All right? So more precisely what this refers to as a decision problem for a set of training examples, whether there exists a parameter value W there that would correctly map the training examples to the corresponding targets. And that problem is hard. All right? So now we would like to develop an analog to the previous case in the learning context that with much simpler methods, we can still get something very close to the optimal parameter values. So let's look at where the complexity of this problem comes from. So let's take a single training example. Let's keep with the sentence and the corresponding parts. So X is the sentence, Y is the corresponding parse. Now I would like to adjust the scores so that the score for that pair that was given is higher than score for any alternative parse. All right? But there are exponential number of super exponential number of alternative trees here. All right? So you have a huge number of possible constraints that the parameters would have to satisfy in order to generate a proper mapping here. So somehow we would like to get rid of this exponential set here, and there are many avenues to that effect. I'm going to describe one simple one here. All right? So the intuition here is very simple. If we don't want to consider all alternatives here, maybe there is just a small subset of them that we can easily see from the training example and compare the target score to only those small subset of alternatives. So what might that subset be? If you take just the target here, you just generate very close by examples as a candidates. So for example, in terms of parse trees, you might modify a couple of edges in the tree and say all trees that are small modifications of that target are now listed as an alternative here. So no longer an exponential set, but potentially a useful set of alternative targets. All right? Well, now we are enforcing a smaller set of constraints. That means that we have a larger set of parameters that satisfy these constraints. And only some in that set satisfy the whole set of constraints that we started with. All right? So the question is, can we somehow shrink this larger set now back to hopefully a point that perfectly reconstructs the training examples? And the answer is that in some cases, yes, we can. If we have large amount of data, we can actually use just these simple constraints and be guaranteed that they suffice to get the correct scores for this method. All right? There are lots of details here in what cases you can guarantee this, but the intuition is that you have to, the training examples that you have to properly exercise the model so that you explore it from different angles in order to narrow the parameter set down to the correct one. All right? So here's just a simple illustration of what happens in cases where we know that this method will succeed. So the theorem is valid in this case. So what this shows is test error as a function of the number of training examples we have. And the red one is a method estimated with these very simple but extremely fast constraints in comparison to alternatives that are much, much more computationally burdensome. All right? And as you can at least loosely see here, that the cases where it actually applies, the theorem looks very similar to actual practical cases that we might wish to solve. All right? So there are avenues similarly to the inference prediction problem that we can reduce the optimization problem considerably and still do almost equally well as we did before. All right? Any questions about the material so far?
Well, actually, we were asked not to ask you questions during your presentation.
I missed that part. All right. I will continue then. So the last challenge here that I alluded to earlier is dealing with ambiguity. That as you have richer structures, more of them look much like the highest scoring one. So somehow we have to be able to properly deal with that ambiguity. All right. So here are just a couple of examples of ambiguity. Here's a simple sentence, a headline from a newspaper: kids make nutritious snacks, and corresponding parse tree. The problem here is that linguistically, it is actually ambiguous. You don't necessarily know whether the snacks are nutritious or the kids are nutritious. Either the kids prepare the snacks or the kids are prepared as the snacks. So there's an inherent linguistic ambiguity in many cases, similar to other problems. But there's also an ambiguity that may come from the method itself. So even though in cases where linguistically it is unambiguous what the parse should be, the method still generates scores that are ambiguous. All right? So there's many sources for ambiguity, and we have to deal with all of them. Here's another example just in terms of pose estimation. If you put little tags on the body and start moving, you can do motion capture here. If you take one particular frame here and try to reconstruct the pose based on what you see in this 2D picture, then the pose itself is ambiguous. So this is just to highlight that across the board of the examples that I listed earlier, such notions of ambiguity apply. All right? So we have to somehow be able to deal with them. All right? So let's look at the effect of the ambiguity here. So this is just a slightly more compact way of writing the problem before. We have a set of scores for each structure, and we find the highest scoring structure. So this Y could still be your parse tree, as we talked about before. So the method that I suggested before just finds the highest scoring tree as the prediction. All right? And the graph there just shows if you enumerate the structures and the corresponding scores as bars, then there's this case here where there is one dominant structure that would be selected. In such cases, this type of prediction is perfectly valid. All right? So no real ambiguity there. Now it becomes more problematic when there are two or more structures that are almost equally, will receive almost equally high scores. All right? So in this case, this type of prediction method is no longer robust. Little changes in the score, little changes in the input will result in a very different prediction, potentially. All right? So that's one problem. The other problem is that even if the scores won't change, you're still not adequately capturing the fact that there are actually multiple alternative structures. All right? So how would we deal with this problem? A natural way to think about this is in probabilistic terms. All right? I have a set of scores here. I can exponentiate the scores and derive a distribution over all possible, say, parse trees here. All right? So these are just the scores exponentiated. All right? So this would be certainly a typical way to do it from a modeling perspective. The problem is that very often this problem is very hard. All right? If making a single prediction was already quite challenging, summing over all possible super exponential number of structures is even harder problem, often. All right? And in particular, it is this normalization here where you have to sum over their structures that makes this problem very challenging. All right? So the point here is that we would like to have a framework for probabilistic modeling over structures, but we would also want it to be tractable. All right? There are certainly a whole set of approximate methods for approximating exactly this. All right? And some people here working on related problems. What I'm going to propose here is something entirely different. All right? Trying to develop a probabilistic way of representing structures, but in a way that's typically tractable. All right? So let's look at how that might work. All right? So here's a different way of thinking about what the probabilities might mean. We still subscribe to the same way of making predictions. We maximize, get the highest scoring structure. But we don't use just the original scores. We introduce some random noise to those scores. All right? So you introduce some random noise. They modify the scores. You find the highest scoring structure. You get a prediction. You make a different randomization. You get a potentially different structure. All right? So as a result, you are inducing a distribution over the structures by randomizing the scores here. All right? In case where there's only a single maximum here, then this type of randomization typically does nothing interesting. All right? So the well-defined case, nothing really changes. All right? Now, this becomes more interesting when there are multiple alternative high-scoring structures. All right? So now what I'm going to do is to randomize the scores. You select one of those structures. And I'm assuming here that this max problem we can actually solve, even though we cannot sum over the structures. All right? If I randomize differently, then I get the other one as the highest scoring structure. All right? So by randomizing, I am inducing a distribution over structures. And it is a distribution that I can easily sample from. I already presented the way how to sample from them. All right? You randomize, you maximize, and you get a prediction.
But it depends significantly on the model of our random perturbation.
I will get to that. Excellent question. All right, so let's follow this on this level of generality just a little bit and look at what this induced distribution might actually look like. All right, looks very different from the one that we talked about before, the typical one, the Gibbs distribution. But it turns out that if I introduce a particular type of perturbations here for the structures, I can actually reproduce the Gibbs distribution that you saw earlier. All right? So in this case, the perturbations follow an extreme value distribution called Gumbel distribution, and the perturbation is assigned separately for each structure. So you introduce a different perturbation selected independently at random for each of the structures here. All right. In that case, in that setting, the same perturbation model introduces a distribution that's exactly Gibbs. All right. And there's now a different representation for the hard part of the problem, which was solving the normalization constant in the Gibbs-style models. All right. So this seems almost contradictory. I started this story by saying that the Gibbs distribution is typically intractable, and now with a different way of thinking about models, I introduced the Gibbs distribution back. So certainly both can't be exactly true. This cannot be tractable, and in fact, in the way that I'm perturbing here, it is not tractable. It is just an alternative representation, just to highlight that this framework actually does not exclude, it actually contains the previous way of thinking about models. All right? And the problem here is that the perturbations here are assigned to each structure individually, not to components of the structure. All right? So in order to then, as you perturbate scores for each structure, in order to find out which one of them is maximum, you essentially have to enumerate all structures. So that's where the complexity comes back in this way of thinking about it. All right? So the remedy here is to not introduce perturbations that are assigned to each structure separately, but introduce perturbations that mimic how they were, these structures were scored in the first place. All right, so let me introduce that with an example. So here's the parse tree again. Suppose we have a simple arc factored model, so the scores given the sentence are just for each arc individually. So when we introduce a perturbation, we simply modify these scores. All right, so I'm introducing a perturbation for each arc score in the parse. All right, a lot fewer perturbations than for each structure individually. All right, and we saw already that this maximization is actually tractable. As I perturb the arc scores, I'm still in the setting where scores are assigned to each arc separately, and I can perform the maximization. All right, so what I have is a model where it is easy to draw a sample from. All right, and the only constraint for this feasibility here is that the maximization problem prior to perturbation should have been tractable or solvable in the way that I described in the first part, through approximate methods, but find the optimal answer regardless. All right? The only issue here is that the resulting distribution with these more structured scoring is no longer the Gibbs distribution. There's a well-defined distribution here. I can draw easily samples from it, but it is not Gibbs. All right? So why do I want Gibbs distribution in the first place? This is just an illustration of the exponential family of distributions that hopefully at least a good fraction of you are familiar with. And we have a well-defined entropy concept that maximum entropy estimation is dual to maximum likelihood estimation. Gibbs distribution is the distribution that maximizes the entropy subject to some statistics that we may have learned from data and so forth. All right, very nice relationships here that makes this work from a statistical perspective. So I would argue this is why we prefer Gibbs. It turns out, unfortunately, that in many cases this whole framework is not tractable. If I can't sum over the structures, I can't deal with this distribution exactly. I cannot evaluate the entropy, nor can I evaluate the normalization constant or do the maximum likelihood estimation. All right? So everything falls when the sum becomes not tractable. All right? Now the question here is whether there's a corresponding story with this new class of distributions. And indeed there is. You can get exactly the same relationship here, for the most part, with just a slightly different concept of entropy. All right? So here we have, with this new entropy concept, this induced distribution that we can easily sample from is actually the maximum entropy distribution subject to some statistics. All right? We have a surrogate partition function, log partition function there, and these are duals to each other and so on and so forth. All right? So essentially the same picture holds as before, except that we modified one of the concepts slightly. All right? So the advantage here is that all of these can be approximated nicely with unbiased samples, provided that the maximization operation there is tractable. All right? So this is actually very new material. Much of it is unpublished. There is already a part of the story that was independently developed by Papandreou and Yule, and they applied it initially to image segmentation and labeling problems. The framework itself applies all over the place, wherever you might consider Gibbs distribution or wherever the structured prediction methodology has previously been used. Now you can try to consider the set of all structures in a probabilistic fashion rather than just predicting the maximizing one. In particular, there's a key advantage here for some subclasses of combinatorial problems that are known to be tractable. So, for example, bipartite matching, when the scores have sub-modular properties, alignments, and so forth. So not only can we draw the maximizing prediction, but now we can also sample from a valid distribution over such structures. And we are in the process of applying these in many places. So in summary, I tried to highlight challenging problems in structured prediction, the prediction problem itself, how to learn them efficiently from data, and how to revise the way that we are modeling these distributions over structures so that you actually attain tractable probabilistic predictions. And with that, I will take questions. Yes?
I actually misunderstand why the ambiguity is bad for us. If we cannot define the optimality criteria, why we should perturbate some weights? Or
right, so the ambiguity is not bad, it is just challenging computationally. So if there are multiple alternative predictions that you could make, then you have different choices at your disposal. You can select just one of them, all right? That's fine. The problem is that it's not robust. So little changes in your estimation process, you actually prefer potentially an entirely different alternative. So robustness is often a key determinant whether it works well in practice. All right. The other reason is just for adopting probabilistic one is just to have a model that considers all the alternatives, rather than kind of arbitrarily restricting to one of them. Any other questions?
Well, many of us are familiar with your famous variational bound for logistic function. My question is, are there any similar variational methods as an alternative to for example, subgradient optimization in dual decomposition or structural learning, something similar.
Right, so the learning problem itself is in some sense a variational problem. It's an optimization problem, and depending on how broadly you understand the term, any optimization problem is to some degree a variational problem. So now variational methods typically refer to a class where you are using an optimization problem as an approximation to something else. That you can restrict the optimization and then get a solution that approximates the larger optimization problem. There are certainly lots of connections with that view to what I'm proposing here. The problem typically with the other approximate methods like variational or belief propagation or other is, if I go back slightly here, is even though they're trying to capture this variability, there are multiple potentially good alternatives, they fail in different ways. All right? So belief propagation, if that's familiar to you, typically fails in the way that the statistics that it's trying to reconstruct may not correspond to any valid distribution. So those marginal probabilities that it is reconstructing are called pseudo-marginal probabilities for that reason. They may be practically useful in terms of learning these models, but they are harder to interpret as marginals of any distribution. So that's a particular failure mode. In terms of variational methods, more broadly, how they would fail in this case, trying to model the Gibbs distribution, is that they tend to be mode-seeking algorithms. So they are essentially an inner bound approximation. You pick a simpler approximating distribution and try to morph it to approximate the more complex situation. The way it would fail here is that it would essentially concentrate around one of those structures and often completely ignoring the other one and not even knowing that it exists. And there are certainly a lot of things in between these success with this new approach and failures of the others. This is just a motivation for why pursue this different direction. Any other questions?
So you mentioned that you suggest we told that we could use pseudo likelihood optimization during structured learning, right? So can it happen that in this case structured learning will be faster than inference during decision making? Because during the inference we have to use, well, some slower methods like LP-orientation, for example.
Right, so it is possible that with these methods that learning is extremely fast, but the prediction is not.
Because this, I find it a bit paradoxical. Learning becomes faster than inference.
Right, let me, yes, the statement is correct. But let me answer it in this way. Even if you were able to learn the model, how are you going to use it? All right? Even if the learning is fast, it doesn't necessarily give you anything unless you can actually use it for prediction. Sure. All right? So another example where this happens is, say, looking at pairwise Markov random fields. All right? So I get, say, image data, and I'm just modeling it with pairwise Markov random field, and I get lots of images. It is very easy for me to aggregate pairwise statistics over pairs of locations in the image. All right? I can do that extremely fast. All right? That was the learning part.
Okay.
All right?
I got it, yeah.
Those statistics perfectly pinpoint a maximum entropy distribution that's consistent with those marginals. But actually using those statistics for prediction is still very hard.
Yeah, right. And the second question, if we use pseudo likelihood optimization during structured learning, then maybe it is reasonable to use pseudo likelihood maximization during the inference. Because we use it during learning, then shouldn't we use it during inference?
Excellent question. Unfortunately, the answer is no. The reason is that during learning, I have the target. And I can construct that small set of alternative examples that I'm enforcing as a constraint. Now, go to the prediction phase. I have just the input. What's the target around which I construct the small set of candidates?
Well, and if we could use, for example, some analogs of ICM, iteratively conditioned modes, then we could, well, grab somehow the fixed point.
That method that you mentioned is actually a way of locally enforcing constraints in order to get a better answer.
Sure.
But it is a greedy method that may get stuck at some point.
If we use greedy method during learning, then maybe we should use greedy method during inference. We'll use different methods.
Right. Again, excellent question, but I would give a different answer than what you're suggesting. The problem with the greedy method in these both components is that it is not robust. The answer depends on the starting point. All right? So during learning, I may prefer some mode here, and that's how I'm optimizing the parameters. Right. During test time, I am actually starting from a very different mode that I didn't even touch during learning. So my prediction is now unclear how robust it is, right? But there is a sort of a general line of research that tries to couple approximate inference with learning. So essentially use very little inference during training, and that fact alone with certain methods guarantees that you need very little constraints, very few constraints during testing to get the answer that the model implies. All right? So there is certainly significant grain of truth in what you're suggesting. I would just use a more stable alternatives for the methods involved.
Thank you.
Sure. Any other questions? All right. Thank you.